Now we're going to use this example 15.3 to talk about types of errors. So in any hypothesis testing situation, there are two types of errors, mistakes that could be made. Now you cannot avoid these errors, okay? They're due to chance. You could have a bad sample, or the random data is actually not so random. There's lots of things that can go on. You can design the test the best you absolutely can, design the study, everything, but these errors can still occur. So a type 1 error is when we reject the null when it's actually false, when it's actually true. Let me try that again. Type 1 error, we reject the null, H naught, when H sub H naught, the null, is actually true. And that's a false alarm. So for instance, if you take a COVID test and it comes back positive, but you actually don't have COVID, that's a false alarm. Type 2 is you fail to reject the null, H naught, when the null is actually false. That's a missed opportunity. So thinking about these in general, the way I start this chart is I think about, okay, I decide to reject the null. I'm going to look and say what is in each of these columns and the rows. The columns in reality null is false, in reality null is true, in reality null is false. I decide to reject the null. I decide to not reject the null. So if I decide to reject the null, okay, and the null is false, that's great. I rejected it and I should have. I'm happy, no error. If I decide to not reject the null and it's actually true, that's great. I didn't reject it and it's true. Fantastic. But if I decide to reject the null and in reality it is true, this is a type 1 error. I decide to not reject the null, but in reality the null is false. This is a type 2 error. Now explain what a type 1 error means in the context of this example. What potential consequence of making a type 1 error would occur here? So this is with the batting power. Type 1. So, okay, he actually is a 0.25 batter, so he has not improved and it's rejected. So the manager thinks he's improved, but he hasn't. What could happen as a consequence? Well, he could get a raise that he actually doesn't deserve. It's a false alarm. He didn't deserve the raise, but he got it. So that is type 1 error in this context. So he is 0.25 batter, but it is rejected. On the other hand, a type 2 error, what is that in this situation, in this context, and what's the potential consequence of making a type 2 error? Well, he actually is better. He is better than 0.25, but no evidence was found. But there's no evidence that he has improved. This is bad for the player. No raise, even though he deserved one. Now, let's think about supposing that the batter makes 9 hits in 20 at bat. What is the exact binomial p-value for this performance? If the manager were making a decision at a 1% significance level, what would his decision be? So we're supposing that the manager is going to give him 20 times at bat with appropriate rest to show that, hey, I did improve. All right. So X, this is going to be the random variable, is the number of hits in 20 at bat. This is binomial, n equals 20 and p equals 0.25. And we're interested in how unusual it would be to get 9 or better. And there we go. There's my p-value. And I'm just doing this using technology. I will say X is binomial with n being 20 and p being 0.25, because remember, that's what he is originally. There we go. We want to show that he's doing better. So do we reject with the p-value of 0.0409 at a 1% significance level? Well, let's see. Nope, we failed to reject. Okay, so we don't reject the null. But in fact, we do know that he has improved. All right, we know it for a fact that he has improved. So this is a type 2 error. What would the decision be at the 5% significance level? Well, let's see, we got 0.409, comparing it to 0.5. Well, this time it's less than. We reject the null here, and he gets his raise. There is no error, okay? Because we know that um, that he actually, like this, it said up here that he actually has improved. He just needs to show that he's improved. So there's no error in E. Now, when would the batter have a better chance, theoretically, of convincing the manager that he has improved? If the manager uses a larger significance level or a smaller one? Well, we see right here the larger, because that's what happened in D and E. It's a more liberal use of the data. G, when would the batter have a better chance, theoretically, of convincing the manager that he has improved? If he gets 20 times at bat or if he gets 40? Now, assuming that he has improved, that he's getting adequate rest in between those times at bat, theoretically, if you really are doing better, then more chances you'll be able to show that you actually are doing better. So more times at bat is better. The margin of error goes down because as n goes up. When would the batter have a better chance theoretically of convincing the manager that he has improved? If he is now a 0.333 hitter or a 0.4 hitter? Well, it's when he's 0.4. Remember, we want him to be further away from the null in that more in that tail. And remember, in this case, we're comparing to 0.25. Okay, 0.4 is further away. This leads us to talking about statistical power of a test. Statistical power is a good thing. It refers to the probability of rejecting the null when the null is false. Okay, and that's what we want to happen. With small sample size, a significance test may fail to detect an effect that may really be present because the test isn't powerful enough to get it right. So power is that probability of correctly rejecting a false null. So let's see if these statements are true or false. Increasing sample size increases power. Definitely, okay? Makes it better. Increasing significant level increases power. Yeah, because we're more likely to reject that null. Sounds good. Increasing the effect size. Effect size in this case is how far from the null we are. Like with the batter, 0.4 is further away than 0.33 is from 0.25. So increasing the effect size increases power. True. So those are all true examples or true statements of how to increase statistical power.